And welcome back to a series I'm doing in complex analysis. The problem that we're going to do today comes from a University of Michigan analysis exam from a couple years back. And let's dive right in. So we have some function f. It's from the disk to itself. So this is the notation I use for the disk. And it's an analytic function, which means we can represent it by its power series. So if we write that out, maybe we call it a to the n, a sub n, and z to the n. And we want to know that for any r between 0 and 1, this expression holds. So let's break it down a little bit and look at the parts. So we have a sum, and we have the same a to the n's here as we did in the power series representation. We're going to take the moduli of these a to the n, square that, and then it looks like this power series evaluated at r too, so that same r to the 2n. If we take that infinite sum, it's going to be equal to what looks like the average value, so I say that because we have this 1 over 2 pi integral from 0 to 2 pi of the modulus of this f squared. So we're doing this kind of theta integral where we're integrating around some arc, and it looks like this r is the commonality here, and somehow these an's translate into this integral. So that's the first problem. And then the second part is to prove that this sum, now we don't have an r, we just replace r by 1, is convergent. Okay, so I wanted to do this problem in part because it was kind of tricky, at least for me, and some of the ways I tried to solve it just really didn't pan out at first, so I wanted to go over those first. The generalized Cauchy integral formula, for instance. So you might think that because in the problem statement we have this integral, we have this f inside the integral, and we have these an's, and we also know that each of the an's is really just the nth derivative of f evaluated at 0, so the nth derivative of f evaluated at 0 over n factorial. That's what each of these an's really is. If we know that, then maybe there's some way to link the Cauchy integral formula back, but I didn't really get anywhere with that. Similarly, the mean value property. So then on the right-hand side, like I said, we're kind of taking the average value, right? The average value of this f, the modulus of it, right? But that doesn't really seem to pan out either. And then the last thing I kind of thought was the Cauchy-Schwarz inequality, because we have a sum and we have these squares, but that's also kind of misleading and really doesn't give you anything of value. So with all those not working, typically it means that there's something even more basic that you're just missing. And in my case, it was that I was missing this simple fact that the modulus squared of a complex number z is equal to z times its complex conjugate. So just this simple fact alone is really basically enough to solve the problem. So let's take a look at part 1 and see kind of what I mean. So we want to kind of rewrite this integral now using this fact we just discussed. So let's go ahead and do that. So we have 1 over 2 pi, integral from 0 to 2 pi, and then we write out f r e to the I theta times f r e to the I theta conjugate d theta. Okay, well, the other thing we know about f is that we know we have an expression for it in terms of its power series. So it might be a little cumbersome, but let's go ahead and try and write that out. So the first part is 1 over 2 pi, the integral, and then we have, like we have in the problem setup, the sum from n equals 0 to infinity of these an's. And then we replace z by this value here, this r e to the I theta. So it's going to be r to the n, e to the n I theta, right? Because we're just raising z to the nth power. And then we take the conjugate of f again, but we don't want to make the mistake of using n twice, rather. So let's use m instead, just a different kind of index. We have am, and then the same exact thing, r to the m, e to the m I theta, and we take the conjugate of all that with respect to theta. So this integral is all with respect to theta. Okay. So now we know that conjugation is a linear function, and that means we can distribute this conjugation over our sum. So let's go ahead and do that and take a look at what that looks like. So we put a bar there. R is a real number, so nothing to do there. And then conjugating on the unit circle, right, which is where this e to the mi theta term lives, is the same thing as putting it to the minus power. So it's e to the m minus m I theta. And that's a useful fact as well if you want to check me on that. Okay, so we have a little something to say, but it's still pretty messy. The other nice thing is that we're on this compact region where we know these series converge. So what can we do? Well, we can bring them outside of the integral so long as they don't have a theta term in them, right? Because this integral is with respect to theta. So let's write that out. So it's still going to be kind of messy, but let's just trust in the process for now and see what that gets us. So we get a sub n, r to the n, times now our m sum, a m bar, r to the n, also to infinity, and then times on the inside, well, we have this e to the n I theta and e to the minus m I theta. So we can combine these terms to get e to the n minus m, that quantity times I theta with respect to theta. Okay, so we have this really horribly ugly thing right now, but maybe, just maybe, we can get it to be a little bit simpler. And the way that we're going to do that is by looking at these terms here in the integrand. So we want to look at two cases, one where m is equal to n, and one where m is not equal to n. So where m is equal to n, right, then this whole integrand is really just, so the integrand, I'll just write it out here, is just e to the 0 t theta, and that's just the same thing as this kind of trivial integral, right? So it's just integrating with respect to theta 0 to 2 pi, which is just 2 pi, right? So that would then cancel with this 1 over 2 pi on the outside, right? So, and then in the case when m is not equal to n, we have an exponential function in here. But we know that in this domain, right, this exponential function is analytic, right, whenever m is not equal to n. So by Cauchy's formula, an analytic function has integral 0, right, when we just take that circular integral, which is what we're doing with respect to theta. So we get 0 and we get 2 pi. That means that all these horrible cross terms that are going to be generated here when n is not equal to m are all just 0, which means that all we have left, the only terms that have value at the very end, are the terms where m is equal to n. So that means we can write out, like I said, we get 2 pi over 2 pi, and then we also get only the terms where n is equal to m, so we don't have to worry about being polite with our indices anymore. We get a sub n times a sub n bar, and then r to the n, r to the n. And I bet you can already see where this is going. We get that sum, this cancels of course, and we use the same property we discussed at the beginning to get back this modulus, and now we have r to the 2n. So that's the end of the first part. So now for part 2. We want to prove that this sum of these squares is convergent. And typically when you're asked to prove one part after another, it's because the two parts are related. So let's kind of take that for granted and see what we can do. So we can rewrite this sum as the limit of things we understand. And at the very least, we can put it in the last problem's terms, and maybe it goes nowhere, but maybe it goes somewhere. So now let's use part 1 of the problem we just did, right? So replacing this awkward sum with a slightly awkward integral, and we get these f r e to the I thetas back, the square, and d theta, right? So this is familiar to us from the first part. But the clutch part from the first piece that we didn't even use is that this f, well, I guess we used it implicitly when we took out the sums from the integral, when we used the integral's linearity like that in the infinite sums. The key piece here is that f is really a function from the disk to itself, right? So it's bounded, namely. And that means that we can just put in the bound for the absolute value. We can bound this integral above. So in other words, we get limit as r approaches 1 from the left of this same integral, 0 to 2 pi. But then we can replace this modulus f by 1 d theta. And of course, this integral becomes 2 pi, which means that we get back 1. Okay, so all this is to say is that this sum here is bounded above by 1. It's a sum of non-negative real numbers, which means that its partial sums are a monotone sequence, which are bounded by this 1, which means that this is convergent. So this boundedness and the fact that it's this sum of these absolute values implies convergence.